All right, let's go back to the beginning. So today, I would like to talk to you today about coronal holes and their role in space weather. I'm coming to you today from NASA Goddard Space Flight Center, which is just outside of Washington, D.C. in the United States. And I work for a company called ASTRA. ASTRA is a space company, and I just started there a couple of months ago. They build small satellites, so I'm pleased to be representing them as well. So I would like to first acknowledge the National Science and Research Society for their role in putting this together, as well as the Nepal Physical Society. Pokhara Astronomical Society sent a few emails early on, and so I appreciate their role in helping all of this. And then, of course, Tribhuvan University for helping educate many people on this call and helping teach physics throughout Nepal. They've been a great partner in all of this. So to begin, I want to spend some time talking about the sun. Of course, that's all why you're all here, but this is really a picture that you're seeing of the entire overview of the sun space system. So this system starts, of course, with the sun, and there are many layers of the sun. We'll walk through those in a second, but it's really the connections between the sun and the earth that make it so important. So that the sun is no longer just an isolated body. It's not just a celestial body that sits in space and exists by itself, but it's part of a larger system that Earth is a part of. And the material that the sun puts out can and will directly affect what's happening here on the ground. So I want to talk to you a little bit about the sun side of things, but we'll start talking a little at the end about how this affects the Earth's space weather, or the space weather affects the Earth itself, and how it can actually impact your own life. But let's zoom in on the sun. So we're going to literally move in and look at the sun a little bit more carefully. So the interior of the sun is made up of many different layers. There's the interior core, which is where the nuclear fusion happens. Then there's a radiative zone where the energy radiates out relatively uninhibited. Then there's a convection zone on top of that. This is all still in the interior of the sun. And the convection zone is really the first layer of the sun that we can actually start to probe with internal helioseismology. So the convective zone is where hot plasma bubbles up from the interior of the sun, gets pushed towards the surface, and then we can actually see the effects of these convection cells on the surface of the sun. And so that's what you see here. On the image here, you see a little cutout with some sunspots on it. That area that I'm highlighting with my mouse, if you can see it, I'm not sure, is really where we start to see features called granulation. And these granulations are little circular type regions that sort of bubble and change with time. That granulation is indicative of that convection. So that convection from the interior, we can actually see it erupting on the surface. Okay, so I spent a real quick amount of time, very short amount of time talking about the solar interior. But where I'm going to spend all the rest of my time is talking about the solar atmosphere. And this is where my research comes in, and this is where I get excited to teach people about what's happening. So I'm going to slow down a little bit and talk about the solar atmosphere, and we'll talk about it for the rest of the time here. So the first layer of the solar atmosphere is the photosphere. So this is the layer of the sun that we see if you go outside and put on solar glasses and look at the sun. It's the part of the sun that the light comes out of that we see here on Earth with our eyes. The photosphere is about 5,600 degrees Kelvin. And it has a few features on it, including sunspots and granulation. Then the next layer up is the chromosphere. The chromosphere is where we start to see solar activity, solar flares. That's the next layer out. And we can start seeing other features such as plage and active regions. And then the outer atmosphere of the sun is called the corona. The corona of the sun is the hottest part of the solar atmosphere, reaching temperatures of millions of degrees. And this is where we start to see the impacts on Earth directly, or we see coronal mass ejections, solar wind, and other features erupting from it. So to talk about this a little bit more, we're going to dive into 3 different features on the sun that can affect space weather and affect the Earth directly. So these three features are active regions, which are areas where there's high magnetic field, there's bright hot plasma, and they can actually erupt. Then there's filaments and prominences, which are quiet features, but they can also erupt because of their unstable nature. And the last one is coronal holes, which is a specialty of mine, and it's these large open magnetic regions. We'll go into each one individually, so if some of these terms are unfamiliar to you, hopefully they'll be more familiar by the end of this lecture. So to begin, I want to just highlight there's different ways of seeing and understanding the sun. So these large-scale structures can be seen with two different types of measurements. There's remote sensing, meaning from a distance. So we're taking pictures of something where you can imagine somebody with a telescope looking at the sun, or a satellite in orbit. But these are all remote sensing, as in they're observing from a distance. And then next, there's in situ measurement, meaning in place. So these measurements happen actually in the body itself. So they're actually sampling the plasma where it happens. So these are satellites and probes. You may have heard of Parker Solar Probe or Solar Orbiter. Those are two recent missions. One was launched by NASA and one was launched by ESA, European Space Agency. And they are both in situ measurements because they are actually flying into the very far out outer atmosphere of the sun and sampling the plasma in place. So these two types of satellites play off each other and help understand actually how the whole solar system or the whole sun system works, the sun, space weather, and then into the Earth. So next, the other thing I want to spend a little bit of time on is light, because light is extremely important for how we understand anything in the sky, but especially our sun. Light is, of course, it's familiar to everybody. You know, in your primary school, you learn about rainbows or colors, and so this is a very familiar sort of idea. But I want to take a little bit of time to talk to you about how the specific light from the sun itself. So on the left here, you see a plot with the rainbow in it, and it's a spectral irradiance. So this is an irradiance, the amount of energy coming from the sun itself. And so as a function of wavelength, as a function of color of light. And so you go up, you can see this steep curve, it peaks, and then there's a long tail out. And superimposed on top of it is a rainbow to get you an idea of the colors of light that are associated with it that we can see, the visible light. And you can quickly see that the sun peaks in irradiance right in between blue and green in the color spectrum. And most of the energy coming from the sun is in the visible light. What's also interesting, though, and the little plot inset at the top shows you that we actually are a little bit blinded by the light because of the Earth's atmosphere. So the plot on top in this inset is actually showing you what the light appears on the ground. The light from the sun appears like on the ground. And you can see that everything is brought down a little bit, but there's also these large gaps in the spectrum, especially as you go out to infrared wavelengths. And these are all caused by water vapor in the Earth's atmosphere, which is why we need to go to space in order to observe the sun in specific wavelengths. However, the visible light and the radio, there are astronomers that study it, but what I'm going to focus on for this talk is specifically the extreme ultraviolet spectrum. So this is far shorter wavelengths than the purple, than violet light that you can see with your eyes. And that's what you see here on the plot on the right, which is the EUV, or extreme ultraviolet part of the spectrum. And you can see that it's fairly, it's fairly complicated. There's a lot of emission lines. There's a lot of elements there that are emitting their specific color of light. But why we study this section of the sun is because extreme ultraviolet light changes significantly during the course of the solar cycle and during the course of different solar events. So while visible light remains mostly constant, in fact, the amount of light coming from the sun is often referred to as the solar constant because of how consistent it is. it changes a little bit during the during the solar cycle, but the major changes come in the extreme ultraviolet flux, the amount of energy coming in the extreme ultraviolet. So that's where we're going to be living for the rest of this. Just a quick side note, I want to put up the solar spectrum really quickly here in visible light, so you can see how complex it is. Those graphs on the side I don't know, they don't really give you a full sense of how complex the solar spectrum is. So here's a high resolution solar spectrum in visible light, and you can see all of the little bars, the little gray bars, and each of those are absorption lines by different elements. So each of these, there's a set of them that represent each physical element that we observe in the sun. So for example, if you wanted to observe hydrogen in the sun, you'd look at the specific wavelength of light for hydrogen, that's up in the red section up here. Or if you wanted to observe calcium, let's say, the calcium appears in the blue section. And so each element has a specific absorption band fingerprint that represents their absorption. We can get into the atomic physics, but that's for another lecture. We can talk about atomic physics later and exactly why there's absorption lines and why it appears like this. But just take my word for it, if you haven't heard about this before, that these absorption patterns are linked to the specific elements. And so what I'm going to do is I'm going to refer to these sort of interchangeably, where I'll say iron 7, for example, or iron 15, and that refers to a specific wavelength of light that iron atom absorbs in. So just kind of get used to some of the terminology. The other thing that solar physicists do, which again is a little bit of a crutch, but it's also something that has a deep-rooted physical nature, is that they associate temperature with height above the atmosphere. As in, if I refer to a temperature on the sun, it specifically refers to a specific layer of the sun as well. And that's what, excuse me. That's what these plots are showing here. So the one on the left is showing the height in kilometers from the photosphere itself, what we were talking about before. And then on the y-axis of the graph is the temperature in logarithmic units. So it's 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th. So as you can see, this temperature region actually changes significantly as you move through the solar atmosphere. So as you start in the photosphere, the temperature actually decreases to a minimum right between the photosphere and the chromosphere. And this temperature minimum is what defines the difference between these two layers of the atmosphere. And then as you progress through the chromosphere, the temperature rises from the low chromosphere through the middle to the high. And then a very interesting thing happens in the transition region between the chromosphere and the corona. All of a sudden, the temperature jumps significantly. It's not just a little bit, but by about an order of magnitude, from 10 to the 5th to about 10 to the 6th. That's an amazing jump. And then throughout the corona, the temperature of the plasma remains about constant. So the reason for this, why does the temperature jump so drastically in between the chromosphere and the corona? Well, that's actually still a mystery. That's one of those open questions on the sun that we don't really know the answer to. There's a couple ideas, there's a couple theories about wave propagation heating the corona, or microflares or nanoflares that erupt all the time. But as a physical practice, we're still trying to understand that. The plot on the left here is just showing you some of those wavelengths of light, those characteristic elements, and where they are observed in the solar atmosphere. So you can see, if you can read the plot, it's showing you where some magnesium lines are, calcium, H alpha. I won't go into this in any greater detail at this point, but what I want you to understand is that there's a link between the elements that are emitting light or absorbing light, the temperature of the solar atmosphere, and the location in terms of the height in the corona above the photosphere. So all of these three things are linked together. And so it makes us able to investigate the sun in a little bit more specific way. The other key element to understanding the sun and how the sun works are magnetic fields. This is incredibly important. And this is the same magnetic fields as you studied in physics class and in high school or college in your first year physics class. It's the same magnetic fields that hold a magnet to your refrigerator or to any piece of metal. You know, you stick a magnet onto a piece of metal and it will hold there. It's the same properties, but on a much, much grander scale. So we study magnetic fields on the sun in two different ways. One is through modeling, and that's what you see on the left, this sort of hairy structure feature of the sun. This is a model of the sun. It's a global field model, potential field extrapolation in 3 dimensions. And you can see that the polarities, the positive polarity in red or orange, and the negative polarity in blue. And you can see this is sort of the topology of the magnetic field lines coming out of the sun, where it's roughly symmetric around the poles, and then it gets very complicated and looped in the center regions. We can also measure the magnetic fields directly, and that's what you see here on the right. On the right is the full line of sight magnetogram, and what that is it's measuring the amount of magnetic field in the photosphere itself. In the next slide, I'll talk to you a little bit about how we do that. But right now, I want you to see that there's these salt and pepper sort of black and white little speckles on the sun. And those also correspond to magnetic field polarities, where the white speckles are magnetic field coming out of the sun toward you in this image. And then the black speckles are the magnetic field going into the sun or away from you in this image. And it's called line of sight because we're only measuring the magnetic fields along the line of sight. We can only measure forward or toward you and back toward the sun or towards yourself in this image. So any more complicated magnetic topology has to be inferred or modeled. You can only measure one direction. There are some newer techniques called vector magnetograms that help disentangle this, but they're still fairly complicated to produce and complicated to interpret. So the magnetic field modeling is what we rely on heavily to understand exactly the topology of the sun. So how do we measure magnetic fields on the sun? If they're so important, they're so critical to understanding how the sun works, how do we actually make these measurements? Well, it's a method called the Zeeman effect. You may have heard of it before. It's one of these common curiosities about elements when you put elements in magnetic fields. It has to do with splitting and fine splitting and hyperfine splitting of the atomic structure. So what you see here is an image of the sunspot with a slit, this slit going down it. There's a black stripe. So you have a sunspot here where the dark center, the umbra, and then the penumbra around it with the kind of granules further away. And then this dark slit here is actually a spectrograph measuring the specific wavelength of light along that slit, and then observing how that line changes, how it splits out, depending on the presence of magnetic field. That's the Zeeman effect in a rough idea. And what you see on the right is the actual measurement of this Zeeman effect as observed. So you have the center core here in the darkest stripe, vertical stripe, and then you have these kind of echoes where you have a secondary and a tertiary stripe that are mirrored off of that. And that's actually the measurement of that fine splitting of the atomic transitions. And the distance between the dark stripe and these other two stripes here you can invert that to understand exactly how strong the magnetic field is that produced that image. So that's really the technique that we go about measuring the magnetic field on the sun. And to create a magnetogram, you go through and you do that everywhere on the sun simultaneously, and to be able to understand exactly that magnetic fields everywhere. So this can only be done in the photosphere and the chromosphere. It's the only place on the sun that we have enough light. There's a new mission that's just coming online. It's a giant telescope in Hawaii that is supposed to measure magnetic fields directly like this in the corona. Hasn't had data yet to do it, but hopefully soon we'll have measurements like this in the corona, but it has never been done so far. So the other piece to understand is that there's two types of Zeeman effect that we can measure. We can measure the polarization of light to understand the longitudinal Zeeman effect or the transverse Zeeman effects, which is linear light. I'm not going to spend too much more time on this because I want to move on to other features of the sun. But what I want you to understand here is that because there are these complicated loops of magnetic structure on the sun, like you see in this diagram on the bottom of a sunspot, where you have these stripes or these lines coming out, showing you what a magnetic field might look like coming out of a sunspot. And the magnetic field is anything but parallel or straight or easy to understand. And so by measuring both the circular polarization of light as well as the linear polarization of light, we can start to piece together this vector nature of the magnetic fields, how they actually move, how they bend, and how they change on the surface of the sun. But let's jump right ahead and talk about observations, because observations are a little easier to show you in pictures rather than equations. So on the left, we have a white light image of the solar photosphere. This is from the Solar Dynamics Observatory. And so what you would see, this is just the same sort of white light that you would get if you went outside and put a filter on a telescope and looked at the sun. You can see that there are these little clusters of black dots. These are sunspots. We've observed sunspots as humanity for thousands of years. I think the Chinese were the first to do it more than 1,000 years ago. But they were first recorded in a systematic way back in the 1700s, where there's been a catalog of sunspot number and appearance on the sun since about 1700. But it's pretty exciting because we've known about these as humans for much, much longer than that. So, and then on the right is the corresponding magnetic field measurements, the magnetograms of this sunspot, or of this photosphere here. So you can see that there's some interesting correlations between the two, that where there's dark spots on the sun, there are also strong regions of magnetic field. So there's a spot in sort of the upper right-hand quadrant of the white light image, that orange disk. There's a little spot cluster there. And then if you look at about the same location on the magnetogram image, there's this little bipole region where there's a white part and a black part. They're a little cluster, a little bipole. So what that's representing is that there's two strong magnetic fields that are right next to each other, one going into the sun and one coming out of the sun. That's what solar activity is all about, is having these strong magnetic fields that are pushed in together and packed in close next to each other. And when you get that sort of configuration where there's magnetic fields that are butting up against each other, that's when you can get energy buildup and eruption off of that. So let's just do a little rhetorical question. You don't need to answer this. If we were in person, I'd ask somebody to answer it. But we'll just do a rhetorical question. So you don't need to answer this, but I want you to think about that. So if we just have white light images and magnetograms, how do we know where the magnetic fields are in the corona or other places in the atmosphere? It's a good question. So the answer to that, like I said a little bit before, is physical extrapolation, running a physical model of how the magnetic fields will propagate through the sun, and then images of the corona as well. So some of these magnetic field lines are actually outlined by images in the corona. So let me show you an example of that. Okay, so we go back to that same magnetogram that we were looking at just a second ago with the photosphere, where we saw spots line up with regions of intense magnetic fields. That's what you see on the left. And on the right now is an image in extreme ultraviolet in 171 angstroms, or 17.1 nanometers of light. So this is an iron line, so this corresponds to an element iron. And you can see, if you have a high enough resolution, or if you can zoom in on your screen, you can see all these little loops and these fine fan loops coming out of the sun, as well as where there was a sunspot before, there's now a bright region in the corona with these kind of loop structures on top of that. So what you're seeing here is plasma that's being heated from the photosphere through the chromosphere into the corona. And as the plasma is heated, eventually, based on the dynamics of the plasma itself and the magnetic fields, the plasma is trapped in the magnetic field lines of the sun and actually are bound up into it. So this plasma property is called the plasma beta property. If you've done any sort of plasma physics, that's the same plasma beta that you learn about in the theory. And as the plasma beta drops below 1, you get this phenomenon where the magnetic fields are now binding the plasma into them themselves. And so this property makes it possible for us to understand where these magnetic fields are by observing these lines on the sun, these magnetic field lines on the sun. So one more thing that we need to discuss before we move on to one of my more favorite topics of coronal holes are filaments. Okay, so filaments are these dark channels that we see here on the disk of the sun. So this is an image in H alpha. So this is a hydrogen alpha line from the ground. This is taken from Big Bear Solar Observatory. And you can see that you can see bright active regions. You can see little sunspots here, little dark sunspots. But then there are these long, elongated cloud-like structures that are dark that sit on top of the sun, the solar surface. These are solar filaments. What solar filaments are these quiet structures where there's cool plasma sitting in the sun, but they're lofted above the surface of the sun, being trapped in those same magnetic loops that we saw earlier in the corona. So what's happening is that there's these cool plasma that is trapped in the magnetic field and is unable to escape back down to the sun as in its current configuration. And so it forms these great giant structures that stretch across the surface of the sun and are held to the surface of the sun in the magnetic structures. But then if something happens where they break or they get disrupted, then all of a sudden, all of this energy can be released and can actually propagate towards Earth. All right. So we've gone through a little bit about sunspots, a little bit about active regions, touched a tad about on solar filaments. But what I'm going to spend the rest of the time on is talking about coronal holes. So coronal holes are the third major type of activity, solar activity that can affect the Earth, that can be geoaffective. So what you're seeing here, this animation, this is our first observation of coronal holes. So this is from Skylab's. It was one of the early space stations, Skylab's Apollo Space Telescope from 1973. They were taking X-ray images of the sun, and something shocking happened, which was it looked like there were pieces of the sun entirely missing in X-ray. The sun looks bright except for this large feature right in the middle, this dark feature. And so they started to call those coronal holes because it seemed like it was just missing plasma. Well, in fact, these features were theorized back in 1957. A guy called Waldmeyer theorized that these structures could exist on the sun, but they had never been observed. And so there was just theory at that point until 1973. And so this ability to look at the sun from space really revolutionized our understanding of how the sun works and how that sun-Earth system behaves. So solar coronal holes, or coronal holes, simultaneously refer to three different physical phenomena that they're all related. They're all similar in terms of how they operate together, but they are observed differently. And so this comes back to the idea of in situ versus remote observing. So the first definition of coronal holes is exactly what I just showed you, which are large dark features, large dark patches on the sun. And that's what you see here on the image on the left, or on the right, excuse me, is this large dark feature, this large dark patch in the solar corona. And that's termed a coronal hole. It's a lack of plasma, and you can see it in X-ray or extreme ultraviolet. The second definition is more of an in situ definition. So if you measure the magnetic field in space from a space satellite, what you can see are open magnetic field structures. And what I mean by open are these long, thin, smooth magnetic field lines that extend unimpeded from the surface of the sun to Earth or into space. And when I say unimpeded, I genuinely mean that. I mean, these field lines can go directly from the surface of the sun and connect all the way to Earth. And that's impressive. And so these field lines define what a coronal hole is. And that's the theory definition as well, as these open magnetic field topologies. The last definition is a bit of a historic definition, but we still use it today, and that's low emission off the limb of the sun. So if you make an eclipse, an artificial eclipse or a real solar eclipse, like there's one coming up here at the end of this year in South America, you can see that there's less emission in the corona. There's less fuzziness. There's less of this kind of bright cloud in the corona. And you can kind of see that in this image here with number 3. The edge of the corona, the edge of the sun is quite bright until you get towards a coronal hole, and then it gets quite dim off the side. So those are 3 different definitions. But how they exactly relate to each other is not entirely determined either. They're related, but it's not like you can take 7 open magnetic field lines and make a coronal hole. There's no direct translation from one to another. So lastly, before we talk a little bit more about magnetic fields, I want to get a little bit more terminology out of the way. So I call this zoology because it's really just labeling what we see. But if we look, there are different types of coronal holes, and they have different properties themselves. So the first type of coronal hole that we can see is an equatorial coronal hole. And this is exactly what it sounds like. It exists near the equator. In fact, it exists between plus 55 and minus 55 degrees from the equator. The second type of coronal hole that are out there are polar coronal holes. Okay, so what differentiates equatorial from polar coronal holes are their location, right? Polar coronal holes exist in the poles of the sun. Equatorials exist in the equator of the sun. That's not a big deal. What's also really different is how long they live. So the polar coronal holes, the northern and southern polar coronal holes, can live for decades, or at least a decade, I should say, 10, 15 years even, as a consistent, coherent structure on the sun. Equatorial holes exist only for approximately a few months, up to a year at a time, before they get absorbed back into the sun. So it's this interesting difference where the polar holes are long-lived and very stable. Equatorial holes are a little bit more. All right, so then the third type of coronal hole is called an ephemeral coronal hole. These again, exist in the equator, but they only last for a few days. So one area of active research that I'm doing is trying to understand, are they all made by the same mechanism? Do they all have the same formation mechanism where the polar holes, the equatorial holes, and the ephemeral holes, are they all made by the same type of physical mechanism, or do they have some different origin stories where they actually they appear slightly different from each other? In general, however, all of these coronal holes are made in the same way by magnetic field lines. And so this is sort of a nice schematic here that I'm showing you about how those magnetic field lines form and what they look like. And they all start in the photosphere. In panel A up here, you can see that magnetic field lines, these long field lines here in this drawing, start in the intergranular lanes in the photosphere. And what I was talking to you about before, so these granules are convection cells, and in between the convection cells, these granular lanes are where the magnetic fields originate for these coronal holes. Then, as we move up from the photosphere in panel A to the chromosphere in panel B, you can see that most of the field lines are looping over and actually back down, connect back down to the sun quite quickly. But there's a certain portion that are uninterrupted, and can start propagating further out into the atmosphere from the corona, or from the chromosphere into the corona. And then in panel C, you can see sort of, again, a schematic of what these field lines look like as they move through the corona and out into the heliosphere, out towards Earth. And again, a majority of the field lines near the equator loop back down quite quickly. I mean, within a solar radius from the surface of the sun, they loop back down and connect back to the sun itself. However, in the poles, and actually in all coronal holes, these magnetic field lines extend far away from the sun. In fact, so far away from the sun, we call them open magnetic field lines. So it really, the story starts in the photosphere, but these magnetic field organizations go from the small individual field lines in the photosphere all the way up into this global structure and propagate out into space. All right. So talking a little bit about the low emission off the surface of the sun, or off the limb of the sun in the corona, this can also be seen during a solar eclipse. So if you ever have the opportunity to see a total solar eclipse, please take it. It's amazing. It's an amazing experience to see a total solar eclipse. But you'll see something sort of similar like to this. This is the image of the sun taken in a specific iron line. It's an iron green line that appears green. But what you can see here is that the coronal holes, you can kind of pick them out because they're all of a sudden it gets quite dim around specific portions of the sun that contain these coronal holes. And this is really what the coronal structure looks like if you could just make an eclipse all the time, or what we call a coronagraph. So this is a bit of a historic definition, but it's also something that you can go and observe yourself if you have the opportunity to see a total solar eclipse. All right. So we walked through all these three different definitions. We have dark patches in X-ray and EUV images. We have dim corona off the limb of the sun. And then we have theory, magnetic field modeling. This is a potential field model where we have the magnetic fields highlighted in three different colors. Purple for, I think purple is positive, green is negative, and white is connected back down to the surface of the sun, so both positive and negative. So all three of these features are related together. They all have similarities, and they all have similar origins, but exactly that recipe is still to be determined. So the last little thing I want to go through, just a couple of slides left, is I want to talk to you just a little bit about how they can affect the Earth, and how these coronal holes, or how, in fact, all solar features can affect the Earth, is through what's called the solar wind. So the solar wind is this plasma that's being pushed off the sun all of the time. And in coronal holes is really the origin of the fast solar wind. So the fast solar wind is a specific type of solar wind that have speeds from about 400 to 800 kilometers per second, densities of about 3 particles per centimeter cubed. So that's quite diffuse. There's not a whole lot of material there. The composition is mostly hydrogen and helium, of course, with some ions. Temperature 2 times 10 to the 5th Kelvin, and a small magnetic, or a reasonable magnetic field of about 5 nanotesla. And it has alphanic oscillations. So these are alphane waves. These are magnetic propagating waves that we can observe in the fast solar wind. But how we get that fast solar wind is from the surface of the sun, but also through the rotation of the sun as well. And that's what this diagram on the left is showing you. Is that you have ambient solar wind, so the solar wind that's coming off from all of the quiet sun all the time, just sort of coming off in regular amounts. But then we have little sections of fast solar wind from the coronal holes. And as the sun rotates around, this fast solar wind, which has very low density, is compressed. And so we get this compression factor, which actually ends up speeding up the solar wind as well, so that it's moving at these extremely high speeds of 800 kilometers per second as we get close to the Earth. So how do we know all of this? Well, it's from a in situ measurement. So we sent a satellite. Well, I use we quite broadly. This is from the Europeans. Europe and NASA launched a satellite called Ulysses back in, I think it was the 80s, and made a couple of passes. It was on this crazy orbit where it went all the way out to Saturn. No, it was Jupiter, excuse me. Went out to Jupiter, and got kicked up into a polar orbit, so it was rotating around the pole of the sun, and then went over the pole of the sun and then back out to Jupiter again, and then over the pole of the sun. It made a couple of orbits because it's on about an 8-year orbit to make 8 years to make one orbit. So what you see here is a little plot where if we can observe the sun in situ, we can measure actually the magnetic fields of the sun and the speed of the solar wind. We can get a plot like this. And what we're seeing here is what the speed and the polarity of the solar wind as we go over the pole of the sun. I put a little Earth in here to remind you that the Earth is sitting on this plane here, the central axis, the x-axis here. As you go around in the center axis of the sun, you see that the solar wind is kind of mixed polarity and it's fairly slow. But as they go up over the pole of the sun, Ulysses measured this high, consistent solar wind speed, as well as a consistent polarity. So we have an outward IMF, the polarity of the magnetic fields, or the inward polarity. So let's put this all together. So we have the sun here with coronal holes in the dark patches. We have this little animation here of what's going on in the solar wind. We have looped magnetic field lines. We have all of these particles flowing out from the sun. But we also have measurements that we can take, and we actually can use remote sensing to observe this flow of material coming out of the sun. This is an image, the highly processed image, observing the flow of that solar wind coming out. And then we can stick a satellite, this little satellite that I stuck in there is a cartoon of Parker Solar Probe, the one that's flying right now. And we can actually fly through this material and make measurements. The reason why we want to do that is that if we get this rush of solar wind and it hits the Earth, it can actually cause a reconnection event here in the Earth's own atmosphere, in the magnetosphere of the Earth. And this is not always bad. It causes the aurora, the northern and southern lights, but it can also create all sorts of charges and electricity build up in the Earth's atmosphere itself. And we can measure this direct effect with coronal holes. And that's what the plot is showing here on the bottom is a solar wind speed predicted in blue, measured in black. And you can see that the speed is directly related to the position of the coronal holes. And we can measure that with these in situ measurements. All right. If we look at it, the poles and how they impact the Earth, of course, it can build up ground charges in the Earth itself. It can actually change the electromagnetic structure of the magnetosphere itself, or on geomagnetic field itself on the Earth. And that's what we just want to show you here real quick. Running a little short of time, but is that this index called the KP index in this plot here, it actually measures the magnetic indice of the Earth as a whole, and so it's measured in many different parts around the Earth. And as this coronal hole that I'm showing here rotated into view on May 4th, you can see that a couple days later, as the solar wind hit Earth, you can see that all of a sudden we went from a very quiet KP index all the way to jumping up to a very active one, where things are very active on the sun. All right, so I'm going to move through here really quick and just go on to a summary so I can have time for a few questions. So what I wanted to point out about coronal holes is that they're regions of low emission, they're low flux, they don't have very much emission in EV or X-ray. They're characterized by these open magnetic field line structures. So these magnetic fields that connect all the way from the photosphere of the sun all the way up to the Earth. And the primary source of the fast solar wind. Of course, there's a lot more to say. There's so much more that I wish I could have told you, but I didn't have time to. So here are a couple of resources. Do a screenshot, grab these. There's some good websites on there. If you want to know more about any of this stuff, this is a fantastic resource to go to in terms of looking at images, understanding more about coronal holes, understanding more just about what different observations are taken and what the sun looks like right now. Heliophysics will show that. Of course, if you're a programmer, if you're interested in programming, the SunPy community with the little logo down here on the side is the Python community that is dedicated to analyzing solar events. It's now expanding into Heliopy, which is going to look at all heliospheric events, so more than just the sun. But please contribute if you're interested, or if you want to just do research on your own. It's a great place to start with the Python package. So thank you very much.